Okay, everyone. So last week we introduced vectors and matrices, and we learned a little bit about how we can do some algebra with them, how we can manipulate them. Today we're going to be thinking about how we can apply vectors and matrices to problems in the real world. And there are two main classes of problems that we're going to be focusing on that were covered in the pre-lecture material. I should have a quick show of hands who watched the pre-lecture material. Okay, great. So two classes of problems. One is a linear system. I mean, these are all linear systems, but one are linear systems of equations where, say, we've got two unknowns and we want to work out what those two unknowns are. Now, we can solve these using high school math, using solving them simultaneously. So you might multiply one by something else and then switch things around, subtract one from the other, or substitute them in, and that'll help you figure out what those two unknowns are. But we can also do the same thing using matrices and vectors, and it turns out this is a much more powerful way of doing it, especially when we have many, many more unknowns. The other type, which is, I think, slightly more interesting, is where we can use matrices and vectors to understand population dynamics. So we have dynamical systems, say something like a population that has different age classes, and we want to understand how the population changes over time. And we can do that using these linear systems with matrices and vectors. Okay, so just to run through the pre-lecture material. The pre-lecture material introduced the idea of a linear system. So this is where we have, say, a matrix A, some vector of unknowns X, and some other vector B. And this, if we multiply using our understanding of matrix vector multiplication, we times a matrix by a column vector. If the dimensions are okay, then we end up with a column vector. And so we can write linear systems of equations that are of this form here in this form here. We have a matrix times by our vector of unknowns here, x, y, and whatever we had on the right-hand side as a column vector. So if you're not familiar with what a linear system is something like this, where we've got just scalar coefficients in front of our unknowns, so 2x minus 1 times by y. A nonlinear system would be something that has, say, x squared or x cubed or cosine of y or exponential of y, any of these other things. So we're interested in just these really simple linear systems where we can write them in this form. Okay, so like I said, there are two different types of system that we're going to be interested in. One is going to be of this form where we have some equations like this and we want to find the unknowns. The other is where we are evolving vectors. By that, we mean we have some vector that, say, represents a population, and then our matrix is essentially telling us what's happening to that population every generation. And so we keep applying our matrix over and over and over and again to see what will happen in the long term to that population. Okay, so the lecture went through this example of if you were in a grocery store and someone's buying tomatoes and someone's buying figs, and you're buying different quantities of these things, and you end up getting charged different amounts. Can we work out how much a tomato costs, how much a fig costs? Okay, so we can write them going from these equations here into what's called a vector equation, and then finally into a matrix equation here. The example of a dynamical system was given where we've got juvenile and adults of a species, so this case bears, and we have some rules around how many juveniles are produced per adult, how many adults live to the next year, how many juveniles die, and so on. So we can turn this kind of word problem here into a linear system by, first of all, writing down, okay, how many juveniles are going to be in the next year, so year n plus 1? Well, it's going to be the proportion that survive from this current year minus the proportion that mature plus the number that are born. So we can translate our information from this word problem into an equation, giving us the number of juveniles in the next year based on the number that are in the current year, as well as the number of adults that are around. Likewise, we can have a similar equation for the number of adults in the next year. So we can write this matrix equation here. So we have these just normal equations. So we've got jn plus 1s and jn's and an plus 1s and ans. We can write this as a vector equation. And then again, just like our linear system with the tomatoes and pigs, we can write this as a matrix equation. This one has a slightly different form though. Here, our unknowns are on the left-hand side, this x, and then we have our matrix times by our vector of describing the population at the current time. Okay, so we'll come back to solving that one a little bit later. We're going to focus initially on how do we solve an equation of this type. So if we've got our matrix times by our unknowns is equal to something that we know, so AX is equal to B. Now, we can usually, if we just had scalars, if A, X, and B are all scalars, and we wanted to find X, then we just divide through by A, assuming A is non-zero. And so X is equal to B over A. So that's nice and simple to work out if we've got scalars. We can't do the same with matrices, because if we try to divide by matrix, this doesn't make sense. Remember, the order of multiplication matters. So dividing by something is the same as multiplying by 1 over that something if it's a scalar. We can't get the same thing for a matrix, okay? Because we don't know whether that 1 over is before or after the thing that we'd be multiplying it by, okay? So instead of dividing through by a matrix, we have to find things called inverse matrices. So we need to find a matrix that when we multiply here our A by this B, B times by A goes to something called the identity matrix. And the identity matrix is just zeros everywhere except for ones down the main diagonal. And that just gives you anything that you had there before. So BA disappears and we just end up with this X, which is our unknowns. This matrix B, which was our inverse, and then our little matrix, a little vector B, which we also know. So this is just a matrix times by a vector on the right-hand side, and we can work that out. And then that'll give us our vector X. So knowing the difference between a matrix and an inverse of a matrix and what happens when we multiply those two things together is really important. Like I said, we end up with the identity matrix if we do that. So anything, a matrix times its inverse gives us the identity matrix. And an identity matrix times by anything just gives us the thing that we had before. Okay, so I times by A is A times by I is A as well. Okay, we usually write this inverse matrix as A with a little -1 up next to it. And note that we can only find an inverse of a matrix if it is square. Okay, so a matrix has to be square in order for it to have an inverse. We can't always find inverse matrices though. If we can't, to work out whether we have an inverse of a matrix, we need to look at something called the determinant of that matrix. This is really, really important. We work out the determinant for a 2 by 2 matrix, which is all you're going to really have to worry about in this course, by taking the product of this main diagonal and then subtracting the product of the off diagonal. So that is this form here. And then as long as this determinant is non-zero, then our equation for our inverse is going to be 1 over that determinant times by a matrix with the coefficients moved around a little bit. So we switch the order of the things on the main diagonal, and then we put a minus sign in front of things in the off diagonal. So this is our inverse matrix. It's how we calculate it for a 2 by 2 matrix, and that's all you'll need to know it for a 2 by 2. But if this determinant is equal to 0, we can't divide by 0, which means that we can't find our inverse. And so we have a singular matrix. Okay. And that has an interpretation as well. I just jump to this bit at the end. If we have a singular matrix, what that means is if we try and find a solution to our problem, then our problem doesn't have a solution, or it has an infinite number of solutions. Okay, so if we have, say, these equations here, imagine these are our tomatoes and figs, and we want to find the solution. Well, we can draw these as lines, and the point at which those lines intersect is going to be our solution. Okay, we have a unique solution in this case. In the second example here, I get rid of those. This one here, the second equation is a multiple of the first equation, which actually means that those lines sit on top of each other. Okay, so we can divide this second equation here by 2, and we get the first equation again, which really means that we've just got one equation, 2 unknowns, And so those lines are identical. So that means we don't have enough information to solve this. So in this case, our matrix would be singular, and we'd have what's called a consistent solution in the sense that we have an infinite number of solutions. We just don't have enough information. And this is different from the third type here, where we've got two equations. We end up with a singular matrix again, but this time our solution is inconsistent. So what does that look like geometrically? That would be like having this red line here and this green line here, and they don't intersect. So there's no solution here because these lines don't intersect. So this is the geometric interpretation of what we're doing when we're finding an inverse of a matrix, and then using it to solve a linear system. We're trying to see whether these lines intersect or not. And so where do they intersect? If they don't intersect, are they, or rather, do they intersect everywhere, or do they never intersect? Okay, so these are the different types of outcomes that we can get. So the last thing is that we went through this example of buying produce. So we have a matrix equation, AX is equal to B. This is just taking our simultaneous equations, our linear system, and putting it in matrix form. We can find the determinant. So the product of the elements in the main diagonal is 8. The product of the elements in the off diagonal is 1. So we do 8 minus 1, which is 7. Non-zero, so we can find the inverse of this matrix. We use the formula above to find the inverse of that matrix. And then we can take A times by A inverse, multiply that together, check. We do get the identity matrix. So when we multiply the left-hand side of this equation here, we had AX is equal to B. We multiply it on the left-hand side by the inverse matrix, A inverse. A inverse times by A is just going to be the identity matrix. So that's going to be a little bit like multiplying something by 1. So it's just going to be whatever we had before. So that's X. And we need to do the same to the left and the right-hand side. So we multiply the right-hand side by the inverse of A as well. We do it on the left-hand side. So that means we do A inverse times by the vector B. When we do that, like I said, the left-hand side, this bit here is just going to be the identity matrix. So that will disappear. We're going to have just our vector with our unknowns T and F here equal to some product of a matrix times by a vector. We do that, and then we end up with an equation at the end. So we've got TF is equal to the vector 2, 1. So that means that in this case, tomatoes cost $2 and figs cost $1. Okay. So although it's relatively straightforward if we have just two equations to solve them, maybe like you did in high school, in many real-world problems, maybe we've got hundreds or thousands of unknowns. And so it's impractical to do it like this. But on a computer, we can do it very fast by using this rule. We've got a matrix, find its inverse, and then very quickly we just have a multiplication to find out what our solution is. So it's a very powerful tool that is used all the time. Okay, that's a summary of the pre-lecture material. Does anyone have any questions about anything that I've talked about there? Nope. Okay, we'll do some problems then. Okay, I'm going to work through this first thing here with you. So first of all, we're going to practice building some vector equations. So we've got a linear system here, and we want to turn this into a vector equation. So how do we do that? Well, our unknowns are our x's and y's here. So I know that I'm going to have an x, I'm going to have a y. In fact, I'm going to do the y in a different color. There we go. And I want to take the coefficients that are in front of my x. So here, I've got a 6, and I would have a 1, okay? So I know that my x has to multiply a column vector with a 6 and a 1. Incidentally, the order that I do these things doesn't matter, okay? As long as I'm consistent. So if I put 1 and 6, that's fine. I could just change the order of these equations around. That's okay. But I have to do it for both of my coefficients. So I need to do the same for the y's. I'd also need to do the same on the right-hand side, okay? This is just like switching the order of the equations. It's okay. There's no reason why it has to be 6, 1 rather than 1, 6. I just have to be consistent. Okay, so what do we have for the y? Well, the first equation, we've got a -2. What's the coefficient for y in the second equation? Exactly, there's no y, so this is just 0. And then I take the things that are on the right-hand side. and put them in a vector. So minus 4, 3. Easy as pie. Okay, let's do one more example. So here, again, we've got x's and y's, so I'm going to put an x and a y. What are the coefficients for my x? 1 and 1. And then for y, 1 and minus 1. And then we'll have a 6 and a 7 on the other side. Now, you're only going to have to really work with 2x2 systems in terms of definitely finding things like the inverse and the determinant, because we're not going to talk about how we define this in more dimensions. But we can write down these linear systems, no matter how many dimensions they are, in matrix form. So here we've got a 3x3. It's exactly the same process, okay? So we've got u, v's, and w's here. So for u, what are my coefficients? 1, 1, 2. For v, minus 1, 1, 1. And then for w, 1, 1, minus 3. And then we just have our vector on the right-hand side. Okay, so this is hopefully pretty straightforward. We're just going back and forth between a linear system that's written in equation form and a normal standard form, and then in vector equation form. Okay, so what do we do next? We don't have to necessarily take this intermediate step, but it's getting you guys thinking about how we build these things from first principles. Now what we want to do is want to take those vector equations we've got and put them into matrix form. So like I say, you don't have to put them in vector form before you put them in matrix form, just showing you this intermediate step to see where these matrix equations come from. Okay, so we've got exactly what we had on the previous slide here for those 3 cases. And we want to take each of these vector equations and turn them into matrix equations. So how do we do that? Well, we just used our rules of matrix multiplications. We have our x and y here. This is going to be our vector of unknowns. So I can put them as a vector xy. And then I need to take this vector here, and I know that we're going to have a 6x and a 2x. So that means that when I put my matrix in front of here, I need to put these things in as a column vector. So that 6 and the 2 just goes here. So when we might multiply this out, this 6 gets multiplied by x in the first row, and the 2 gets multiplied by the x when we go on to the second row. Okay, we've got this minus 2 and the 0 for the y, exactly the same here. We need to put the minus 2 and the 0 in as a column vector for the second column. And then we have our right-hand side, minus 4, 3, nothing changes there. So again, the order of these things doesn't matter. I could switch the order of everything here, put what's on the first row on the second row, as long as I'm consistent throughout. It's the same thing. Any idea how, if I've just done this, how I can check that this is the right answer? How do I check that I haven't made a mistake? Just multiply it out, right? So if I multiply it out, and have 6x minus 2y is equal to minus 4. If I go back to my equation up here, I had 6x minus 2y is equal to minus 4. If I then do the second row, I have 2 times by x plus 0 times by y is equal to 3. I've ended up with a 2 here somehow when there shouldn't have been a 2 here. These equations are not the same as they are above. I thought they were. They have, obviously, that should have been a 1 when it was copied over. I will leave it as a 2 here now just because it's consistent on this slide, but That should have been a 1. Anyway, this equation here, 2x plus 0y is equal to 3, gives us, is consistent with this vector equation here, even if it's not consistent with the equation before because that was a mistake. Okay, have a go at writing this one here, the second one as a matrix equation, and then the third one as a matrix equation as well. Okay, let's see how you guys got on. There we go. Okay, so for this one here, you should have had 1, 1, 1 minus 1 times by xy is equal to 6, 7. And at the bottom, we should have had 1, 2, 2 minus 1, 1, 1, 1, 1 minus 3. Times by a vector of unknowns UVW is 0, 3 minus 1, assuming I haven't made a mistake. Okay, so like I said, we don't have to go through this intermediate step of putting them into vector equations. You can just go straight from these equations here down to a matrix form here. The vector form isn't super useful. It's the matrix form that is the thing that's useful. Okay, so that was that first type of system. I want to have a quick go at building the other type of dynamical system. The other type of linear system is a dynamical system, I should say. So this is an example where we've got 2 alleles in a population. And to start off with, we have most of the individuals have allele X, but each generation, 5% of individuals are going to mutate to from X to Y. Okay? So we want to determine a matrix model that tells us how the change in the allele frequencies are going to occur over time. Okay, so we need to first of all define some notation. And whenever you're doing a model like this, you always need to define your notation. Okay, don't just write something down. We should always be very clear. So in this case, I'm going to say let x of t, so x subscript t, be the proportion of individuals who are carrying allele X at generation T. And then likewise, let Y of T be the proportion carrying allele Y at generation T. Okay, so how do we turn this word problem into a matrix model? Well, first of all, we need to write down a linear system of equations that describes the population change. So what do we know? Well, in generation T plus 1, we're going to have the proportion of individuals who were carrying allele X in the previous generation. And we're told that 5% of those individuals will mutate away. So they'll mutate to having the other allele. So that means that we have what we had before, the XT, and we subtract 5%, so 0.05 times by XT. So this is just saying in the next generation, generation T plus 1, how do we work that out? We take what we had in the previous generation, and 5% of those mutate away. What about for Y? Well, we take what we had in the previous generation, YT, and we just add on those ones coming from X. So we're told that 5% of the individuals are mutating from X to Y. They get taken out of here, and they get put into here. So this is just a linear system like we had before, so we can write this as a matrix, just as we did above. So how do we do that? Well, this time, rather than having a matrix equation in the form AX is equal to B, where X is our unknowns, we're now going to have something in the form X is equal to A times by B. Okay, so it's a slightly different way of writing things down. How do we do it? Well, we take our population in the next generation. So this is the thing we want to know. Then we're going to have some matrix of coefficients. And then we're going to take, I don't know what that was. Then we're going to take our vector of the current population, okay? So we're going to assume that we know what the population is at the moment. We want to find out what it is in future. The only thing left to do now is to write in our coefficients. Again, we're just thinking about the rules of matrix multiplication here. What do we need to have? Well, we need to have, bless you, we have 1 times by xt and 1 times by yt. So let's put these in. So we're going to have a 1 times by my xt on the first row. I know in my second row, we're going to have a 1 times by my yt. What else have we got? Well, actually, it's not a 1, is it? Because we've got this here can be written as xt times by 1 minus 0.05. So that's xt times by 0.95. So actually, this one here, we're going to get rid of. We're going to write as a 0.95. Okay. So all I've done here is we had a 1 minus 0.05, which we can write as 0.95. There's no y in this first equation. So we have 0. In the second equation, we've got our yt times by 1. And we've got 0.05 times by our xt. So we write 0.05 and 1 on our second row. Again, this is something that I would always recommend you to do, is once you've written down a linear system, whether it's the type of problem we had before or the type of problem here, we've got a dynamical system now, go back and check your working before you go any further. How do you do that? We just multiply these things out. I know that I should have an xt plus 1 is equal to 0.95 times by xt and 0 times by yt. That gives me my first equation. Okay. Remember that this xt minus 0.05 xt can just be simplified to 0.95 times xt. The second equation, yt plus 1, it's going to be 0.05 times by xt. So that's this bit here. And then plus 1 times by yt, that's this bit here. Okay, so it checks out. You have an ability to check your own answers before you go ahead. So whether it's in an IQ or an OQ or in an exam, I would always recommend you just do the quick multiplication, check that you've got the right thing. Okay, so that's our matrix equation. Now what can we do with it? Well, suppose we're given an initial distribution of individuals who have X and Y alleles. So suppose initially 99% of the population has allele X, 1% has allele Y. What's the distribution going to be like in the second generation? Well, in this case, our T is going to be 1. This is the only thing that's changed, as well as what our X at generation 1 and our Y in generation 1 are. Okay, so what do we do? Well, to work out what the distribution is in generation 2, we need to take our equation above. So we had 0.95, 0, 0.05, and 1 times by what do we have in generation 1? Well, we're told that we have 99% have allele X and 1% have allele Y. So we just need to work this out. This is just matrix vector multiplication. Whoops, don't know what's happened there. There we go. Matrix vector multiplication. Put this down. If we do that, you'll get approximately 0.94 and 0.06. It'll be a little bit under or over these numbers, but it's approximately that, okay? So this tells us going from one generation to the next, how's the distribution of alleles changed? Allele A has approximately dropped to 94%, sorry, allele X has dropped to approximately 94% of the population. Allele Y has increased to roughly 6% of the population. Okay, how about the equation that describes the population after a given number of generations. Okay, so how do we work this out? Well, I'm going to call this a vector vt plus 1, and this vector vt, just for simplicity, and this matrix A. So after 5 generations, well, 5 generations, we want the vector v5. Well, every time, if I take the population generation 1, this is my v1 here, this is my v2 here, and this is my matrix A. If I want to work out what the population is going to be in the 3rd generation, v3, I need to multiply the population in v2 by A. But this, we know, is going to be A times by A v1. Okay, it's recursive. So this is just A squared times by v1. And the same thing applies as we increase the number of generations. So population in generation 5 is going to be A to the power of 5 times by what we had initially, v0. Up to 10 generations, v10. It's going to be A to 10 times by v0. And 1,000, it's going to be A to 1,000 times by v0. I realize slight issue of my notation here. Rather than v2 and v1, this should have been v1 and v0 to be consistent. And change this to v1s. Okay, so we're going to start with our initial population. We usually call our initial population as occurring at time 0, so t is equal to 0. So rather than 1 and 2, I've just switched it to 0 and 1 for consistency below. Okay, so this number here matches the number of powers that we need to take our matrix A to. We times it by our initial population, v0. This will be laborious to do by hand, but very quick to do on a computer. And so we can find out what's happening after 5, 10, 1,000 generations. So we can work out very quickly what is going to be the long-term behavior of this population. And it should be pretty clear that because we've got just mutations flowing from X to Y, eventually X is going to decrease, and Y is going to increase. So allele Y will go to fixation because there's nothing flowing out of Y and there's something flowing out of X. Okay, so over time, this thing here is going to tend towards 0, 1. We'll talk a little bit about other ways in which we can work this out when we talk about eigenvectors and eigenvalues, and these things, which we'll touch on very soon, they tell us about the long-term behavior of a model. We can work it out by just recursively doing it, but if you want to do A to the power of 1,000, I doubt you want to do that by hand. On computers, it's going to be pretty quick, but still, if you've got a very large matrix, this could take a little while. So knowing something about the long-term behavior just by looking at our matrix, rather than having to do these calculations, is a really powerful way of finding out long-term behavior, which we'll talk about in another lecture. Okay, there's a few minutes left. There's a problem like this on the IQ, so I just wanted to go through it here to make sure it's clear what we need to do. So suppose you've got a word problem like this. You want to make a burrito with beans, cheese, and tortilla. And you have some information about the nutrition provided for each of these different ingredients, okay? And you want to work out, well, how much of each of these different ingredients do I need to make a burrito with a certain distribution of with nutrition, okay? So we want a certain amount of protein, a certain amount of carbs, a certain amount of fat in this burrito. How do I do it based on the information I have? Well, we just need to write down an equation or a system of equations for each of these different types of nutrients. So we have protein, we've got carbs, and we've got fat. And what are we told? Well, I'm going to assume that I'm going to let this, the beans be B, the cheese be C, and the tortilla be T. What are we told? Well, we're told that per cup, beans have 16 grams of protein, 40 grams of carbohydrates, and 0 grams of fat. So I'm going to have 16 times by B in our protein equation, 40 times by B in our carbs equation, and 0 times by B in our fat equation. How about for cheese? Well, cheese, we are told we have 26 grams of protein. So we have 26C in our first equation. 48 grams of carbs, so 48C in my second equation. Is that 4? That's 4, not 48, sorry. 4 grams of carbs. And 38 grams of fat. So we have 4C in the second equation for carbs and 38C in the third equation for fat. And then finally, our tortilla, we have 4 grams of protein, 6 grams of carbs, and 2 grams of fat. Okay, so these 3 equations here are just turning the information from above. What is the distribution of nutrients in each of these different ingredients into a set of equations? And we want these to be a certain thing. So we're told here at the bottom that we want 33 grams of protein, 48 grams of carbs, and 21 grams of fat. So we want this top row to be 33, the middle to be 48, and the bottom to be 21. This is just like our linear systems that we had before, right? We've got 3 unknowns here, B, C, and T, the beans, cheese, and the tortilla. We want to work out what quantities of these we need to have in order to have the ideal distribution of nutrients. Okay, so we can write this in matrix form. What's that like in matrix form? Well, we're just going to take those coefficients that we had, 16, 40, 0, 26, 4, 38, 4, 6, and 2. We have our beans, our cheese, and our tortilla. And we have our vector of ideal distribution on the right-hand side. Okay. So again, how would I make sure that this thing here that I've just written down matches these equations above and make sure that I haven't made a mistake? Multiply it out, right? So I'm not going to do that here, but do it in your own time just to check that this thing matches. Okay, so we're told that this thing here is going to be our solution, it's vector I of ingredients. So that's 1 cup of beans, a half a cup of cheese, and 1 cup of tortilla. So how do we work out that this is the ideal solution? Well, what do we have? Well, the only thing of unknowns that we have is this vector here. So we just need to plug this vector of ingredients into where we have this B, C, and this T, and check that when we multiply these things out, we do get this ideal distribution here. So plug in the I for where we have this B, C, and the T, multiply this thing out, and see, do we get 33, 48, and 21 for our distribution of nutrients on the right-hand side? Okay, I've gone through that fairly quickly. I do appreciate that. But seeing as this is something that's on the IQs, I wanted to make sure it's clear as to what you need to do in order to solve that problem, okay? So if you're asked to verify a solution, you need to plug that solution in, multiply it out, and see if you get what you were told you would get, okay? See you on Wednesday.